Okay, طيب. We'll wait for a few seconds, inshallah, and then we'll start promptly at 10:22. طيب, Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to EE201. So today's lecture will be a continuation of what we started last time, which was about voltage and current division, or voltage and current divider circuit. But before going into the details of today's lecture, I'm going to just remind you about homework 1. It's due, inshallah, this Thursday at 11:59. You can access Gradescope. And the instructions are written here. And the assignment is there. So you need to write down your solution and then upload it. For quiz 1, it will be, inshallah, on Wednesday during class time. The material for that is section 1.1 to 2.5. Okay, just going over what we've done last time. If you recall that we stated that in general we don't have a single resistance, but instead we have a combination of resistors. And this combination could be in parallel, in series, or neither parallel nor series. So it turns out if we have a series combination, then the equivalent resistance, so we can lump the contribution of all individual resistances or all individual resistors into a single one. And this single one is called the equivalent resistance, and this equivalent resistance is given by this formula, which is the summation of all individual resistances or resistors. In the case of parallel combination, we have a slightly different configuration, or we have a slightly different formula. And the equivalent resistance, one over the equivalent resistance is given by this one. So just for a mathematical, just to give you a mathematical insight about this formula, this is known as the harmonic mean of the resistors. And last time we started talking about voltage divider circuits, and we stated that, well, if we have a single power supply, then we can extract portion, we can generate a different voltage level depending on the application that we have in mind. For example, if we take our output across R1, then the voltage across R1 is given by this formula, R1 divided by R1 plus R2 multiplied by the voltage source. If we take the output across R2, then the voltage is given by this formula, R2 divided by R1 plus R2. So we have a constant multiplied by the voltage source, a constant less than 1. Constant less than 1 multiplied by the voltage source in the case of the second one, or second voltage, second output. And we know that this constant depends on the values of R1 and R2. Actually, it depends on the ratio of R1 and R2. Okay. Last time we stopped at this example, with this stopped at this exercise, we stated that the resistors that we have, they are not ideal resistors. It means that they come with a tolerance, so the value can deviate within 10%. So we're asked to find the maximum and minimum of voltage V naught. So just to explain the logic behind this, let me just copy this formula and bring it to the next slide, or copy this figure and bring it to the next slide. Okay. So we have R1 and R2. R1 and R2, they have 10% tolerance, which means that R1 can take any value between 0.9 multiplied by 25 kilo ohm to 1.1 multiplied by 25 kilo ohm. Similarly, R2 can take any value between 0.9 multiplied by 100 kilo ohm to 1.1 multiplied by 100 kilo ohm. So depending on those values, we can get either a maximum or minimum. We can get different values of the output. This is not desired, but this is the reality, and we have to live with it. We have to cope with it. So we have to design our circuits to accommodate such a swing. Maybe if you have a sensitive application, you should use resistors with better tolerance, meaning that the tolerance is something in the range of 1% or even less. So if you recall, the V output is given by this formula. And in this case, what we have is something very interesting. So the maximum value that we have is the maximum output occurs when R2 is maximum, R1 is minimum. Again, R2 is maximum, R1 is minimum. So we are maximizing the numerator and minimizing the denominator. In this case, so let's write it down. So the maximum R2 is 1.1 multiplied by 100 kilo ohm. R1 is 0.9 multiplied by 25 kilo ohms. This is the condition for the maximum. Ahmed, can you hold on until I'm done with the exercise? Because I cannot answer all questions, otherwise we will not finish anything today. Okay. So R2 is the minimum is when R2 is minimum, R1 is maximum. So you're minimizing the numerator and you're maximizing the denominator. So now we have the conditions for the maximum and the conditions for the maximum and minimum. So knowing this condition, we can easily substitute the values of the output and of the output, and from that we know the maximum output voltage and the minimum output voltage. So the maximum output voltage is, we have 110 kilo ohm. This is R2 at its maximum. R1 at its minimum, 22.5. Multiplied by 100. And this is 83.02 volts. V1 minimum is when V output, when R2 is in its minimum value, R1 is in maximum value, multiplied by 100, and the result is 76.6 volt. So you can see that they're almost like 7.58 difference, 7.58 voltage, 7.58 volt difference between the two, the maximum and the minimum, which depends on the application. This could be tolerated or not. Ahmed, your question?
دكتور وشو اللي 0.9 وال1.1؟
Okay, so if I said like the maximum is this one has plus or minus 10% tolerance, it means that the value of this one could be 10% greater than 100 kilo ohm or 10% less than 100 kilo ohm. So if I tell you that something is 10% less than the actual value, so that value is 0.9 multiplied by the actual value. Think about it from a financial point of view. If I give you a 10% discount and I sell you something for 100 riyal, it means that you need to take 100 multiplied by 0.9, and this will give you the value. Okay, very good. Clear?
Clear, yes.
Leila?
ايه دكتور، هذا 0.9 وال 1.1 هذه بالنسبة لل 100 كيلو اوم. طيب ال 25 اوم ال 10% tolerance المفروض يختلف ولا؟
No, it's you're talking about it percentage wise. So
percentage للفاليو حقها، الفاليو حق 25.
Yes, that's what happens here. So 0.9, which is 90% of 25, is 22.5. So if you take 25 multiplied by 0.9, you'll get 22.5.
Okay.
Good. Okay, excellent. من في واحد اوكي
انا رفعت يدي بس فهمت الان. شكرا لك.
Okay, good. Okay, we can generalize this case to include more than a single resistance, more than actually two voltage levels. So if you recall here, we have two resistors. So what happens if we have n number of resistors? It turns out that the situation is exactly the same. The only difference here is I need to, instead of dividing by the summation of 2, I need to divide by the equivalent, which is the summation of all resistors. So think about it this way. We have R1, R2, so on until you reach Rj. Rn minus 1, Rn, and this one is V. Vj will be Rj divided by R1 until Rn multiplied by V. This is equal to Vg. So this formula is known as the voltage divider law. And remember, for voltage divider law, there's a very important condition here. So the resistors must be connected in series, which means that each individual resistance must have a different voltage level. If you have resistors connected in parallel, then voltage divider law does not apply. Why is that?
Because it's the same across the circuit.
Yes, because the voltage level is exactly the same across all of them. Okay. Any question or proceed? Alhamdulillah.
اي دكتور، بالنسبة للقانون الحين شلون احدد الريزستور الاول عن الثاني؟ عن طريق الكرنت من الفولتج.
It doesn't matter which resistor. I mean, the resistor that you are interested in is the one that you're gonna put in the numerator. The resistors that you don't care about, or the remaining resistors, will be including the one that you care about, as in the denominator. ميداني.
Yes, Doctor. So Rj and R1 and the remaining resistors are connected in series or parallel?
No, series. They have to be in series. If they are in parallel, it means that they have the same value, the same voltage.
So why did we put Rj and the numerator?
Because we're interested in finding the voltage across Vj, across Rj here.
And it's included also in the denominator?
Yes.
Okay.
Rj over R are equivalent. If n equals to 2, then we go back to the original formula here that we derived. R1 plus R2. Abdulkarim, so
Doctor, what if we have two resistors in series in between? Like I got RJ1 and RJ2. In the numerator, I put RJ1 plus RJ2.
What do you mean by two resistors in series?
You see RJ?
Yes.
What if I have two resistors, RJ1 and RJ2, between the positive and negative?
So you want to take the voltage level across two resistors, right?
Yes. Yes.
Instead of one? Yes. Yes, you can add them, because you can add the voltage due to the first one and the voltage due to the first two. And if you add them, you should add they have a common denominator. So the denominator should be the same, which is R equivalent. The numerator is different. We'll take an example once we're done with the current division, because I will take an example that includes both, and the idea will be, inshallah, clearer. Okay. So we had a situation, or if you remember, we talked about a circuit that divides the voltage, which requires having resistors in series. Now let's talk about a circuit that divides current, which again requires, we cannot use a series combination, because remember that if you have two resistors connected in series, they must share the same current. This is a simple result of Kirchhoff's current law. So what happens here, if you have two resistors connected in parallel, if Is is the current, then at this junction, Is will have two ways to go, one through R1 and the other one is through R2. It will go through both ways. The only difference here is the amount of current that is going to flow across through R1 and the amount of current that's going to flow through R2, which depends actually on the resistance of both of them. So in order to simplify the calculations here, so we need to come up with an expression that relates I1 or I2 to the total current, which is Is in our case, and to the resistors, or the ratio of resistors, R1 and R2. In order to do that, let's apply Ohm's law. So let's apply So if we apply Ohm's law, then we can write I1 as V divided by R1. I2 is V divided by R2. Since R1 and R2 are connected in parallel, so we must have the same voltage. Also, if I combine them, if you recall from the previous class, if I combine them in parallel, because they are in parallel, so their equivalent resistance is going to be R1, R2, R1 plus R2. Then I have three expressions for the voltage. So expressions for V. V could be from this equation I1 multiplied by R1. It could be from this equation I2 multiplied by R2. It could be from this figure here. This is IS, R1, R2, R1 plus R2 multiplied by IS. So I have three expressions for the voltage. So now I can use what I know here to write I1 and I2 in terms of R1, R2, and IS. If I do that, I will write V divided by R1. This is going to give me R2, R1 plus R2, IS. I2 will be V divided by R2, R1. So notice one thing here. If you recall, in the case of the voltage divider circuit, we have in the numerator, we have the resistor that we are interested in finding the voltage across. And in the denominator, the summation. In the case of current divider circuit, it's the opposite. So in the numerator, we have the resistor that we are not interested in, divided by the summation. Here, for example, I1, we are interested in finding I1. I1 is the current passing through R1. So in the numerator, we have R2. In the denominator, we have the summation. So this is very important. Or this makes a lot of sense, because if R2 is high compared to R1, you would expect that more current is going to flow in R1. So that's why you have the opposite. So the current that's going to flow through the resistor that we are interested in depends actually on whether the opposite, whether the other resistor is bigger than our resistor or smaller than that. Okay, Ahmed.
دكتور، هل يعتمد على العدد ولا ما يعتمد على عدد الريزستورز؟ يعني إذا كان عندي ثنتين مثلا.
Then we'll come to it.
Okay.
Okay, very good. Okay. So now let's see what happens if we have the following circuit. So in the following circuit, we are asked to find the power through the 6 ohm resistor shown below. So we have a 6 ohm resistor, and we are interested in finding the power dissipated by that 6 ohm resistor. So let me ask you this question. Let me start with Mohammed. What do you need to find the power here for the 6 ohm resistor?
The power, I can find it by the current and the resistor itself. I square R.
Okay, exactly. So you need to find the current.
Yeah.
So in order to find the current,
Okay.
So in order to find the find the power, you need to find the current, because you know the resistance or the voltage actually. But in this case, it's better to find the current. Not really, actually, you can find the voltage as well. But anyhow, this is depending on the current divider circuit. So we are assuming that we're interested in finding the current. So the current, if I call this the current flowing through the 6 ohm resistor I naught. So I need to find I naught. So what is it exactly I need to do here to find I naught?
I will start by finding.
Okay, this is good. I am looking for some
Okay.
to increase the pressure. Thank you. Yasser?
Yes, first we need to combine the resistors in parallel, 6 and 4.
Yes.
And it will be 2.4.
Yes.
And then we will combine the 1.6 and 2.4, and they will be in series.
Okay, excellent. Okay, so let me. Okay, very good. So following the suggestion that Yasser mentioned, is I have 1.6 ohm, then I combined 4 and 6. So the equivalent resistance is 2.4. And here, now I lost the current I naught, but I will keep it in mind. So now what should I do? Let me go with Ibrahim.
We should combine 2.4 with 1.6.
Okay.
So that we end up with the 2 resistance.
Okay, very good. So if we end up with 2 resistors, then type 1.6, this should be 4. Type, okay. طيب عمر صلاح, now what should I do? I want to
now,
find
now we can use the divider.
Okay. So I want,
as the law says that if you're interested in the M4, so you put 16 up, and then the sum.
Okay, multiplied
by the source, which is 10.
10. In this case, the result is 8 amperes. So you see that 8 ampere will flow through the 4 ohm resistor, and the remaining 2 amperes will flow through the 16 ohm resistor. So the resistor with the branch with the least resistance will have more current. Okay. Hassan Al Abdullah. Now what should he do? Hassan?
Sorry, my mic was muted.
Okay.
I think we should get back to split for the 4 ohm resistors, resistor to 2 back.
Yes, exactly. So we need to go back to the original circuit here. So we know that this is 10. This is going to be 16. And this is 1.6 for and we know that we found I1 to be 8 amperes. So now I need to find I naught. So in order to find I naught, Ziad, what would be I naught?
KCL. Or do we use again the same division for current?
Yes, we need to use exactly the same technique. So the current divider circuit. So I naught will be the resistors that we are not interested in, which is 4, divided by 4 plus 6 multiplied by the total current, what is the total current in this case?
8.
8. Remember 8, not 10.
But I have a comment about.
Okay, what's your comment?
We took the long way.
Okay, because I want to explore. I want to make sure that you understand the current, the concept that we're trying to achieve. Okay, 3.2. So in this case, I'm left with the power, and who's gonna help me with the power? Ahmed Al-Hamad. Ahmed Al-Hamad, what's the power?
It's I square times R.
Okay, I squared multiplied by R, so it's going to be 3.2 squared multiplied by 6 equals to 6,144 watts. Okay, very good. So we saw a sequential application of current divider circuit. So now back to the question that Ahmed Al-Nafi mentioned, that what happens if I have more than 2 resistors? It turns out if you have more than 2 resistors, then you can extend the current divider circuit, but you need to be careful here. So first of all, these resistors must be connected in parallel. If they are connected in series, it means that they have the same currents, and there is no point for dividing. The current cannot be divided; it will be the same. The second thing is the current that's passing through the branch Ij should be R equivalent divided by Rj multiplied by the total current. So if you recall, for the case of the voltage, it's exactly the opposite. So the resistor that we are interested in divided by the equivalent multiplied by the total. Here, it's the equivalent divided by the resistors that we are interested in multiplied by the total. Amar, yes.
Sir, can we use it for the if there is only 2?
Yes.
Instead of the previous
yes,
one?
if you use it, if there is only 2, you substitute R equivalent. This is a good exercise here. So R equivalent will be R1, R2, R1 plus R2. And if we are interested, say, like about the current passing through R2, then we need to divide by R2, I. So in this case, you will see that R2 will cancel R2, and you will end up with R1 in the numerator, R1 plus R2, I, which is exactly what we found. Clear? Okay, very good. Rahim, yes.
Doctor, in the previous example, we had one resistor connected in series. Should we include it with us in the equivalent resistance?
No. In this case, what do you mean? Which one?
The 1.6.
No, with the 1.6 here, we cannot apply the 1.6 here. We cannot use it if we are trying to directly relate I naught to the 10 ohm, so the 10 ampere source.
So here it cannot be found by that method.
No, because we have 1.6. Okay. So now let's take this very interesting exercise, and in this exercise we are trying to actually apply both voltage divider law and current divider law. So we want to find I naught and V naught. So clearly we can find I naught using current divider law and V naught using voltage divider law. So let me take this circuit and copy it to the next page. And let me just further simplify it. So what I will do, I will combine all resistors in series just for the time being. So if I have I have 8, 36 plus 44 is 80, 10, then 50, 40 plus 10 plus 30, this is 80. And then I have 24. So here I lost V naught, but I'm not interested in V naught at the moment. I'm interested in I naught. So let me look for a new name. Okay. عدنان قرعاوي. عدنان.
We can find the voltage.
Not really. I need to apply the current divider circuit here, the current divider law.
Then we use من القانون نفسه R equivalent over the current passing through the resistor multiplied by I,
which is 8. In this case, R equivalent will be okay, let me write it this way. R equivalent will be 1 over 80 plus 1 over 10 plus 1 over 80 plus 1 over 24 to the power negative 1, which is 6 ohm. So I naught will be 6 divided by 24 multiplied by 8, and the result is 2 ohms. Okay. طيب. So the result now is 2 ampere. So the next step that I need to do is what? Okay, let me see a new name here. The same. Okay, عمر صلاح. دقيقة عمر هذه.
We can just use Ohm's law to find the voltage across the 24 resistor.
Yes, exactly. So if we use the voltage across the 24 ohm resistor, is 24 multiplied by 2, and this is going to give me 48 volts. And what should I use it for? عبد الله الجريري.
We use it to find the V node.
Okay, how?
We use the equation.
Which equation?
The Rj over Reqv.
Exactly. So I have 40 now. 10. Brought it back to the original circuit. And then 30. And this one is 48 volts. So V naught will be 30, 10, plus 40 multiplied by 48, and the result is 18 volts. Okay, very good. Okay, now we found V naught and I naught. So let's move on to the following exercise. And for that exercise, I want you to pay attention. And this is very important exercise. And there are a lot of concepts here that we need to be careful with. So the first one is, or in this exercise, we are asked to find V naught and the total power dissipated in the following circuit. So let's consider finding V naught. By this time, we know we are strongly familiar with finding the power dissipated by the circuit. So we need to find the voltage and the current. So for V naught, it's very important to notice one thing here. Let me copy it and let me write it down. So it's very critical, very important. Okay, just realize that no current is passing through the 2 kilo ohm and 4 kilo ohm resistor. Which means that I can redraw the circuit ignoring those. So 10K, 15K, 3 kilo ohm, and 12 kilo ohm. And this one is V naught. So if I call this node A, this node B, then V naught will be VA minus VB. So the node A with respect to ground is the one with a higher potential. The node B with respect to the ground is the one with the lower potential. So now all what I'm left with is to find the voltage VA and the voltage V naught, the voltage VB. So in order to do that, I need to apply KCL. I need to apply a current divider law here to find I1 and I2. From the current divider law, I can actually find the voltage using Ohm's law. And once I found the voltage, I can use this expression to find V naught. So if I apply current divider law, I will get, first of all, the equivalent resistance is going to be 15 plus 10, they are connected in series. 12 plus 3, they are connected in series. And the series combinations are in parallel. So it's going to be 15 plus 10 is 25. 12 plus 3 is 15. Then 25K plus 15K. And the result is 9.5 375 kilo. Then I1, which is the current passing through the branch that contains 15K and 10K, will be the equivalent resistance. Now, Omar, this is the application of the general formula divided by the resistor that we are interested in, which is 25. Multiplied by the total current, which is 18 milli. And the result is 6.75 milliampere. I2, 9.375. Should be 15. You can do that, or you can apply just simply KCL here. 11.25. So notice one thing here. So the current is flowing from down to up, not up from down, because here we're kind of going through. So this is the total current, and the total current will split into two currents, I1 and I2. I2 are flowing from this node to the upper node. So the direction of the current flow is from the bottom node to the top node. Okay. Now, if I apply Ohm's law, I should keep in mind VA, which is, let me call it 15K, is going to be, we have the current in the opposite direction. We have the voltage that we are interested in is in the opposite direction with respect to the current, so we have to have a negative sign here. Or the current is entering from the location of the low potential to the location of high potential. So this is going to give me minus 101.25 volts. VB will be minus I2 multiplied by 12K, and this is going to give me minus 135 volts. So now I found VA and VB. V naught is VA minus VB, and if I take the difference, it's going to be 33.75 volts. Okay, any questions, Shabab? Abdullah and Yusuf?
Doctor, when we use KCL, the node down, the bottom, shouldn't I2 will be less than 18 because it's split?
It should be, yeah, it's 18.
But split, its voltage should be less than 18.
So 11.25 plus 6.75, how much is it?
Oh, okay, I got it now, thank you.
Good. Is Sleh?
Doctor, why is VB negative?
Because in both cases we have VB is, let me use different color here. So this is VB, and this one is VA. So the current is entering the negative to the positive. Adnan, yes.
Doctor, how do I know if VA is across 50 resistors resistance or the 10?
Because here I'm asked about to find the voltage here. So this one positive means the voltage at this node with respect to the ground, and this one is negative is the voltage of this node with respect to the ground.
Yes, but what I mean is, why isn't it minus I1 multiplied by 10, not 15?
Because this is a good question, and the logic behind this is you're caring about. First of all, it depends on what will be the reference point in your case. The reference point is whether you use this one or that one, you should get the same answer.
Okay.
But I always prefer to have the reference point in the bottom. Okay, let's move on. Ahmed al-Nafi, if it's a quick question, please ask. If it's going to take a while, let's wait.
Doctor, I want to ask about the sign, the sign, yeah, for the V.
Yes.
How you consider that the minus is down and the plus is up?
Because we are told here that V naught is given by this formula, or V naught have the following configuration.
Okay.
Okay. Okay, very good. So now let's start chapter 4. In chapter 4, we are interested in, so we developed the theory in chapter 1, chapter 2, and chapter 3. And chapter 4 is more about a systematic way of solving problems. So far, the circuits that we have are simple. They're not complicated, but oftentimes you are faced with complicated circuits. In order to solve them, you need to actually find a systematic way of solving complicated circuits. So cannot rely on simple applications. So we saw, for example, most of the circuits that we have, they're simple. We're not asked to invert any large matrices, etc. So these circuits are much simpler. But the reality is not like this. The reality is we have a rather complicated circuit. So we need to find a systematic way of solving a complicated circuit. So we cannot just use Ohm's law, KVL and KCL. You can still use them, but instead of like solving the problem in a single page, you might need to solve it in 2 or 3 pages, which is not a practical way. So the systematic way, we're lucky to have 2 systematic approaches of solving circuits. The first one is called the node voltage method, and the second one is known as the mesh current method. And the way these methods were utilized were used by introducing some sort of like intermediate variables or intermediate parameters. And those intermediate parameters further simplify the analysis. So let's see. If we have a node voltage method, then we're trying to find the voltage at each node. And remember, keep in mind that we're trying to use KCL at each node. We'll come to the difference between node and essential nodes. So the output is going to be a node voltage. So if you know the voltage and you know the resistance, can you find the current?
Yeah.
Okay, by applying Ohm's law. Exactly. So in this method, the node voltage method, which is the method that we're going to start with, is we're trying to specify some specific nodes, some kind of like special nodes, and we find the voltage on these special nodes. And from the voltage of these special nodes and the value of the resistance, we can find the current. For the mesh current method is the opposite. So we're trying to find the currents on each loop. We can use KVL to find this current. And if I know the current on each loop, I can find the voltage just by applying Ohm's law. So the moral of the story is the following. We can either use a systematic way. We have two options. One method is actually allowing us to find the current, and from the current we can find the voltage. The other method is allowing us to find the voltage, and from the voltage we can find the current. Okay, so this is just like a brief introduction. We'll deep dive into them in the following lectures. But before starting analyzing circuits in a systematic way, so let's throw some definitions, some terminologies here. So the first one is planar and non-planar circuit. This is just a definition of stating the difference between planar and non-planar circuit. So if we have a circuit that we can draw or redraw in a plane without any crossing branches, then this is called planar circuit. If we have an example of this one, this is a planar circuit. Yes, we have crossing branches, but if we can slightly modify the connection, bring this one, where is it? No, bring this connector here and connect it this way, we can get a planar circuit. Non-planar circuit is something like this. So non-planar circuit cannot be drawn or redrawn in a plane without any crossing branches. The reason for introducing those is actually the first method that we're going to study is called the node voltage method. And the node voltage method is applied for both planar and non-planar. For the mesh current method, the one that we're going to study, inshallah, in maybe next week, we have to have planar circuits. Okay. We'll come to these terms when we solve this exercise. So in this exercise, it's asking us to identify all nodes. So you may ask yourself, what is the definition of the node? Going back to the table here, a node is a point where two or more circuit elements can join. We can see here that, just copy it here. We can see here that A is a point where two circuit elements are connected. B is a point where two circuit elements are connected. C, D, E, F, and G, they are all nodes. So in this case, we have all nodes. So the nodes that we have, again, nodes are points where two or more circuit elements are connected. So we have A, B, C, D, E, F, and G. Okay. The second definition, or the second thing that we need to find, is essential nodes. So what is the difference between nodes and essential nodes? There's a tiny difference here. It says that a node an essential node is actually a node. So, but instead of, we put some limitation on the number of elements that are connected here. So where 3 or more circuit elements are joined together. It means that every node, every essential node is a node, but not every node is an essential node. So going back to the circuit, it says here, an essential node is a node where 3 or more circuit elements are connected. So let's double check here. Node A connects 2 circuit elements, V1 and V2, V1 and R1. So node A is not an essential node. Node B is actually an essential node because it connects R1 with R5, with R7, and with the current source. So the first one is B. Node C is actually an essential node because it's the point where V1, V2, and R2 V1, V2, and R2 join. So it connects 3 circuit elements. So this is an essential node. Node D is not an essential node because it only connects R1, R2, and R3. Node E is an essential node because it connects R3, R5, and R6. Node F is not an essential node because it connects V2 and R4. So node G is actually an essential node because it connects R4, R6, R7, and I. So out of the 7 nodes that we have, 4 of them are essential nodes. The third definition that we are interested in is the definition of a branch. So what do we mean by branch? So a branch is a trace joining basic circuit element with no element included more than once. I'm sorry, this is a path. A branch is a path that connects 2 nodes. So we have 7 nodes. So assuming that there should be more than 6 branches. And let's see here. So node A is connected with node B through R1. Node A connected through node C through V1. So R1 and V1 are branches. Or yes, R1 and V1 are branches in this case. Node B is connected to, again, node A for R1, which is included, connected to node E with R5, and connected to node G with R7, and connected to G also with I. Going to node C is we include its connection with node A. So it's connected with node B with R2. It's connected with node F with V2. Now we go to node D. Node D is connected to C with R2, which is included. It's connected to node E with R3. Now we go to node E. Node E is connected to node B with R5, which we included. Connected to node D with R3, which we included, and connected to node G with R6. Node F is connected to node C with V2, which we included, and connected to node G with R4. So now node G is connected to node E through R6, which we included, connected to node B with R7, which we included, connected to B with I, which we included, and connected to node F with R4, which we included. So in total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 branches here. So we have 10 branches. Now, we can go a step further and ask about essential branches here. So essential branches are, again, a subclass of branches, but instead of connecting nodes, you connect, instead of connecting two nodes, you connect two essential nodes without passing through any essential node. So it's okay to pass through a node, but it's not okay to pass through an essential node. So let's see what happens here. So starting from the essential node of B and C, so they are connected through B1, R1. So this is an essential branch. Then node C is connected to node E. Node C, which is an essential node, connected to node E, which is again an essential node, through R2, R3. Then node C is connected to an essential node, which is G, through V2, R4. Then going to node B, which is an essential node, is connected to node E, which is again an essential node, through R5. Node B is also connected to node G through R7. Both of them are essential nodes. And node B is also connected to node G through I, which is an essential node. Did they include R6? Okay. Node E is also connected to node G, which is an essential node, through R6. So you can see here that we have 1, 2, 3, 4, 5, 6, 7. So we have 10 essential nodes, 10 nodes, and out of these 10 nodes, we have 7 essential nodes. Yes, Hassan.
Doctor, the node above R7, is that, I mean, is that a node or?
It's all part of node B here.
Why is not separated? Why?
Okay, so to see the difference here, if you take this point and you find the voltage difference between this point and that point, what will be the voltage difference here? Will they have the same voltage?
Yes.
Yes.
Oh, okay.
If they have the same voltage, then they are the same node.
Okay, thank you.
Okay. Very good. The Karim?
So doctor, if I can remove node B and put the other one, the one above R7 instead of it, that would also give me the same potential difference?
All of this is node B.
Oh, okay.
All of this is node B.
Okay, thank you.
And all of this is node G. The mesh, all meshes. So a mesh is what? First of all, a loop is about last node is the same as starting node. So we start from a node and we end at the same node. Mesh is a loop that does not enclose any other loops. So looking into this this figure, for example, you see that if you assume that this one is a loop, which is actually a loop, this one includes two internal loops. See this one and this one. So yes, it's a loop, but it's not a mesh, because a mesh is a loop that does not enclose any loop. So according to the circuit we have, meshes are V1, R1, R5, R3, and R2. This is the first mesh. The second mesh is V2, R2. So the first one was this one. Second one is this one. The third one is going to be that one, and the fourth one is that one as well. So the third one is R6, R5, R7, and the last one is R7. Of course, there are more than there are 4 meshes, but the number of loops is greater than 4. Okay, 2 paths that are not loops or essential branches. Let's ignore the last 2 parts. Okay, let me solve it. 2 paths that are not loops or essential branches. So what's the definition of a path? A path is a trace that joining basic element with no element included more than once. So in this case, to violate this one, you can ensure that anything that's not a loop or essential branches is a path, is what's required. And the last one is 2 loops that are not meshes. So for example, the one that we explained, this one is not a mesh because it enclosed a loop. This one also is not a mesh because it encloses 2 loops, this one and that one. Okay. So now with the definitions, probably the very important definitions are those 2: essential branches, mesh, and essential node. Because this is the definition we're going to use for mesh current method. And this one is the definition that we're going to use for node voltage. Right, okay. I have 2 minutes. Let's pause for a question. Ahmed, let's take your question after we're done. So in order to construct the solution, so I need to find the branch currents. So in this case, in the previous case, I have 10 branches, but one of them has a current source, so the current is known. So in total, I have B branches, which is 9 in this case. To find them, I need to construct a number B linearly independent equations. So I have, in our case here, I have 9 equations, 9 current that I need to know. So I have to construct 9 linearly independent equations. Now, if I have n nodes, I can derive n minus 1 independent equation by applying KCL at any set of n-1 nodes. The remaining b minus n-1 can be found by applying KCL. So think about it in terms of this exercise, of this circuit that we studied. So we have 10 branches and we have 7 nodes. So if we apply KCL at each node, then KCL is going to give us n-1, which is 6 independent equations. The 7th one is actually depends on one of the equations. So the remaining 4 equations. So I need 10 equations to solve this one. The remaining 4 equations can be derived using KVL. So in total, I have 10 equations to solve, 10 equations and 10 unknowns. Here, it's simpler because this one is a current source, so we know the value of the current source usually. So I have 9 equations and 9 unknowns. This is a lot. Again, even though this is a 9 equation and 9 unknowns, this is a large number of equations that I need to solve. Okay, let's see. Shabab, I will explain this, but feel free to leave, because if I stop here, it will be hard to continue next class, because I need to start the whole discussion again. So it will be recorded, so feel free to leave. I will not take more than 2 or 3 minutes, but we are behind in the syllabus. Well, now if instead of, remember, if I use number of branches, number of nodes, I will end up with large number of equations. In this case, 10 equations. If instead I use essential branches and essential nodes, usually essential branches are much less than essential nodes. Essential branches are less than branches. Essential nodes are less than nodes. So I will have KCL is going to give me NE, which is number of essential branches minus 1 independent equations. The remaining equations can be found using KVL. So going back to the circuit that we studied, we have 7 essential branches compared to 10 branches. We have 4 essential nodes compared to 7 nodes. Then KCL is going to give me 3 equations, 3 independent equations. The remaining 4 equations can be found using KVL. So in total, I have 7 equations. So just by using the essential branches, I reduce the number of equations from 10 to 7, which is better than 10. But the issue here is, like, I still have to have to solve out equation. So it turns out I can simplify this calculation if I introduce intermediate variables. And those intermediate variables are the node voltage equations, the node voltage and the mesh current. So if I introduce the node voltage, I will get NE, the number of essential node minus 1 equations to solve. I will get the node voltage after all. Then I can apply Ohm's law to find the remaining components. If I apply the mesh currents, I will get PE minus NE minus 1 equation, which is in this case 4 equation in the previous example. So I will stop here. I will see what I can do for the parts that I missed. But that's all for today. And I apologize for stepping over time. But we are behind the syllabus and we're going to take a quiz. The quiz is going to be during the class time. Okay, any question? Yes, Ahmed.
دكتور ممكن تعيد الفرق بين اللوب والمش؟
طيب. A loop is a mesh is a part of a loop, or like a subclass of a loop. So a loop can be, for example, here. If we start from this part, from F, so we start at node F, and we move around the circuit until we reach point F again. Okay? Clear, Ahmed? This is a loop.
Yes. Yes.
But here is the issue with that loop. There is a loop inside of it. There are actually two. If I start from this one, I can have a loop inside of it. This is the first one. The second one is this one. So it encloses another, it's actually enclosed two loops.
Okay, can't I say the circuit, the brown circuit that you have drawn before, which is start from F and end to F. Can't I call it mesh?
No.
Because it has two circuits inside it.
Yes, two loops inside it.
Thanks.
Ali?
Doctor, I didn't understand the branches and the essential branches.
So branch is a path that connects two circuit elements. صح?
Yes.
Okay. This branch is a path that connects two nodes. So in this case, if I have, say, for example, I have node A, صح?
Yes.
And node B.
Yeah.
So this one is a branch.
So the element inside is the branch or what?
No, yeah, you can assume that the element inside is part of the branch.
Okay.
Okay. Now this is the branch. The question is, what is the essential branch? So the essential branch is simply a branch, but instead of connecting a node with another node, you connect essential node with an essential node.
Okay.
In this case, this is an essential node. So this one is a branch because it connects two essential nodes. This one also a branch because it's connected to a essential node. But this one, I'm sorry, this one is essential, these are essential branches, but this one is not an essential branches. Why?
Because E is not essential. No. Yeah, it's clear now. Thank you, Doctor.
Fahad? Fahad, you're muted.
Can you hear me, Doctor?
Yes. Yes.
Can we say that all meshes are loops?
All meshes are loops. Yes.
But we can't say that it's the other way around, right? That
Exactly.
a loop is not always a mesh.
Exactly.
Okay. Thank you, Doctor.
Riyad?
The last part in the session about the number of equations.
Yes.
There was two ways to get the same number, but what is the difference when we get 7 using KCL and KVL and essential node and mesh? What's the difference if they're both 7?
No, the first one is if we use nodes and branches, we can get 10 equations and 10 nodes.
10 and 7. Okay.
And if we use essential nodes and essential branches, we'll get 7 equations.
I see.
Okay, thank you all.